This is the flipped version of lecture number 8 in the Year 1 Roehampton University course Creativity and Computing. The theme for today is problem solving, and I want to explore that in a relatively broad sort of way. During the lecture you'll actually get on and code some problems up in Scratch, which hopefully you'll be able to incorporate into your game. But let's start by looking at a little bit of the background, a little bit of the theory behind this. At the beginning of the national curriculum, the current edition, the 99 edition, we have a definition there of problem solving. The key skill of problem solving involves pupils developing the skill strategies that will help them to solve the problems they face in learning and in life. And isn't that at the heart of the primary curriculum? Shouldn't we be doing that? Problem solving includes the skills of identifying and understanding a problem, planning ways to solve a problem, monitoring progress in tackling a problem, and reviewing solutions to the problem, all of which, of course, can happen across the whole swathe of the curriculum. I'm curious to know why there's perhaps not as much of this as there probably should be or ought to be in the primary curriculum. How come when children do problem solving it becomes relatively simple, trivial problems? These big skills here are things which they miss out on. Ewan McIntosh talks a lot about problem finding, and I think that's a really interesting territory of, rather than giving children problems to solve, let them find the problems and then go about tackling those. We're looking at mobile app development with our current Year 3s, and we've looked at the Apps for Good project, much of which focuses on finding problems to which a mobile phone app might well be an interesting and creative solution. As it says, all subjects provide pupils with opportunities to respond to the challenges of problems and to plan, test, modify and review progress needed to achieve particular outcomes. I think this is particularly fertile territory for ICT, but all subjects can bring this in, and particularly I'd suggest those which have a design focus, because the design challenge is very much one of solving problems. And I hope you've already had that experience with your Scratch programming of having to solve problems in order to get Scratch to do things for you. So again, what I want to look at in this lecture is how you overcome some of those challenges. I want to give you 3 problems to start with, and we'll spend some of the time during the actual face-to-face session of the lecture having a go at solving these. This is an old classic maths investigation. The challenge here is to get the red frogs from the left of the screen over to the right of the screen, and the green frogs from the right of the screen over to the left of the screen. The rules are very, very simple, and there's a little game I've coded up inside BYOB Scratch to let us experiment with that. So click on the green flag, and let's see what happens here. We can click on this frog, and it moves 1 square across. This frog again moves 1 square across. This frog moves 1 square across, and this frog, can't actually jump over those frogs. That's such a shame. Let's start all over again. 1 frog over there. Another frog jumps over, so it can jump over 1 frog at a time, but not 2 frogs. And then we can do that, certainly. Then we can do that. I'm stuck here, but I can move that one. So that's made a little bit more progress. I'll let you have a play with that during the lecture, or you can download it into BYOB Scratch, which is a variant of Scratch, and have a play with that yourself. I need to use BYOB so as to be able to pass parameters to procedures here, which is coming in Scratch too, but isn't there in the version which you're using at the moment. Okay, then you have these sorts of lovely situation problems here. And I have happy memories of playing this sort of game at secondary school. I'm not sure about primary school, so this is a moderately gruesome one. Again, this is something which we can spend some time trying to solve on Friday. 2 men went into a restaurant. They both ordered the same dish from the menu. So they tasted it. One of the men went outside the restaurant and shot himself, as I say, rather gruesome. Why? And you're allowed to ask me yes or no questions about that, and hopefully try and figure out what's happening in that slightly bizarre, slightly gruesome situation. This is a classic problem. This is called the Monty Hall problem, and I'm just going to load that up into BYOB here. So I'll replace that project with this project. And in the Monty Hall problem, what you have to do is guess where the secret treasure is hidden. So we will start the game here. I think actually we just click on a door. So it's not behind door 2. Is it behind door 1? Is it behind door 3? Let's have a look. Yay! It's there. I've started the game from scratch. No treasure there. Let's click on, do we stay or do we swap? That's the game. That's how the game is set up. So the Monty Hall game show, there's a secret treasure. There's a big car behind one of the 3 doors, and there are 2 dustbins behind the other 2. You get to choose your door, and then Monty Hall, the game show host, opens one of the other 2 doors, knowing as he does where the secret treasure is hidden, shows you the dustbin, and then you have to decide whether you're going to stay on the door that you've already picked or swap to another door. I'm going to swap at this point. I win. Let's have another go. Let's pick that door. It's not there. Do I stay or do I swap? I'm going to swap again. Oh, I lost on that one. Pick that door. Stay or swap. Pick that door. Stay or swap. Okay, I'm not doing particularly well. Pick that door. Stay or swap. I'm going to swap. So that's got me a 60% success rate. Let's start the game again. Stay or swap, stay. Yay! Pick that door, stay or swap. Oh well. Pick that door, stay or swap, let's stay. Oh, this is not going so well. Stay or swap, stay. Okay, so the question is the best strategy to stay? Is the best strategy to swap? The problem then is explaining why that strategy is the best, or perhaps you're of the view that it doesn't actually matter which strategy you pick, and there's an interesting problem, trying to decide which strategy is best or whether there's any difference between those strategies. Let's move on. So back to the PowerPoint slides. I asked you to read the couple of chapters from the Jonathan text about learning to solve problems, and you hopefully will have found this list of different approaches to problem solving, or different types of problem, I should say, that we present to children in a school setting. So we have that sort of logical problem, we have the sort of can you execute a particular algorithm, the situational or story problem here, rule using problems, so problems which are defined using particular rules, all of which are relatively low level skills. Then we get into slightly more interesting territory of trying to, of a problem which requires the student who's trying to solve it to come up with, to make some decisions and see the consequences of those decisions. If you think back to the stuff which we did with the Fighting Fantasy game books, that non-linear narrative stuff, a lot of that is around decision-making, problem solving. And then the sort of thing which you encounter a huge amount when you're programming a computer is troubleshooting, is fixing problems that you encounter because, it's not worked as you expected it to. How do you sort of overcome those difficulties? We'll talk a little more about that in a moment. And then the more interesting stuff of the troubleshooting can be relatively straightforward, but actually when you're met with a cluster of symptoms and then diagnosing what's caused that cluster of symptoms, what the cause of a collection of particular behaviours is, and then coming to a solution for that. And then more strategic things. And then the interesting problem-based learning often means this sort of case analysis. Let me tell you a story, and then you look at how you might have reacted to that situation yourself and solve that. And then, into interesting territory with starting from, not quite a blank sheet of paper, but perhaps a list of requirements and designing solutions to that. And I think a lot of ICT education, we can move into exactly that territory of designing a solution to something which is often phrased in terms of a problem. Using the word solution suggests that it is a problem. There's something which we're trying to achieve, and then the things which have very rarely a simple solution, the dilemma where either solution or either option is almost equally bad. Case-based instruction or problem-based learning is something which happens a lot in other professions. So medics or business administration students, or a whole cluster of or lawyers are often now taught using this sort of case-based approach, where we present a particular real-world problem, and the learning comes about through understanding that problem and coming up with solutions to that problem, rather than the sort of let me give you the body of knowledge and then I'll present you with the problem to solve to show that you've mastered that. You actually acquire the body of knowledge through solving those problems. And I think programming lends itself to that. I'm not actually teaching you a huge amount of computer science here, but I'm giving you plenty of opportunity to learn some computer science, some programming skills as you go about solving this problem of making your own computer game. So the quote, teaching begins not with a theoretical exegesis, an exposition of the domain concepts, but with a real problem, Rather than learning and forgetting all about a field before being allowed to solve a meaningful problem, case-based instruction is based on the belief that what you learn whilst trying to solve a complex problem, you'll better comprehend and retain for much longer. The most important rationale for case-based instruction is that it at least simulates the kind of activity that students are preparing for. Now, I wonder if this is something which you're encountering on the course that you're studying, the program as a whole. Are we talking about real situations that you encounter in the classroom, or is it at the moment a case of us giving you lots of sort of theoretical understanding of the process of education, the processes of learning and teaching, and then later on when you come to be out on placement you'll have actual meaningful problems that you have to solve drawing on that knowledge? Could one swap the whole thing round and talk about the situation, show you some of those situations, say, okay, this is the case, the problem. Now, what are the reasons for that, and how would you go about solving that problem or working in that particular case? As I say, this is something which is particularly current in a whole range of professional vocational training. Nurses, doctors, lawyers, business management courses are often based around this problem-based or case-based approach. I'm curious about your experience, whether there's been any element of that on your teacher training course as you've encountered it so far. More interestingly still, is this an approach which might work in the classroom? Let's pick a subject, pick geography. Could you teach geography concepts by presenting a series of problems, a series of cases to the children in a class, and then inviting them to relate to those cases, to explore those cases, to investigate those problems, and then come up with a solution to that? Or does one need to do it the traditional way of, here is the body of knowledge, now apply that to solving these problems? It's an interesting exercise, and I appreciate your thoughts on that. There was, for a couple of, whilst we had Teachers TV, this lovely interactive exercise in behaviour management in a primary school classroom. Showed you a video and said, okay, which of these 3 children who are misbehaving during the lesson do you want to go and intervene with? What are your options when it comes to that intervention? Unfortunately, Teachers TV was closed down because of a lack of funding from central government. And whilst many of the video resources have been preserved, regrettably this interactive activity doesn't appear to have been. So I can tell you about it, but unfortunately you won't have the opportunity to play with that this time round. Okay, let's move back into sort of programming territory. And one of the things which you will have to deal with as you're developing your game, but also across the whole range of ICT in school, is this sort of troubleshooting situation. As Jonathan says, troubleshooting is among the most commonly experienced kinds of problem solving in the professional world. Problems that are most completely and accurately recalled are those that are most difficult to solve, because the problem solver is more conceptually engaged in the process. So you learn so much through trying to fix things. There's a great quote from Richard Sennett which actually addresses that directly, about understanding is something which is developed through that process of trying to fix things. And Jonathan recommends this particular 5-stage approach, which is a sensible and identify what the problem is, construct a mental model, Piagetian schema coming into this, of what's actually going on here, how does that fault arise, and that mental model is necessary if you're going to have any hope of diagnosing the problem. Think about what a doctor does when met with a collection of symptoms with a patient presenting themselves. They have this mental model of how the body works, how people can be healthy, and then of course using that mental model and the set of symptoms that are presented, they diagnose the problem, then of course implement a solution and actually keep track of that and record the solution. Same thing's going to go on when you encounter problems with your programming, so you need to be quite specific in identifying what the fault is. You need a mental model of how Scratch is working so that you can understand how to solve the problem. So you're diagnosing exactly what the fault, what has caused that fault, and then of course fixing it is relatively easy. It would be nice if you kept track of some of those results, and part of your module score is about that sort of iterative process of development. What were the problems you encountered and how did you overcome them? That's one of the things I am asking you to submit some evidence for. What else is worth saying about this? This also applies to teaching, doesn't it? If something goes wrong in one of your lessons, identifying the fault, using your mental model of how education, how learning, how teaching works, diagnosing the problem, what has actually caused this particular problem, using that mental schema, and then you find your solution. And it's nice if your lesson evaluations keep track of that, so you have got some record of what you've learned through that process. Think back to our experience at the primary school that we went and visited. That problem of these computers are not all gonna, the symptom, the fault that we encountered was that the screen refresh was so slow that it became impossible for the children to create something on screen. So my mental model of that relied on the knowledge that we were doing this in a thin client model, that we had all of the software running on a big computer somewhere streamed across a network. And that informed my diagnosis of the problem, and my solution was to shut down half of the laptops so that we were using less of the bandwidth. And of course then we had another solution to the problem, which was actually stop doing some of the drawing and concentrate on the programming in the second session. But you can do it with children as well. This is not just about technology. My lessons aren't working, or my behaviour management strategy isn't working. Yes, identify the fault, but you're going to rely on your theoretical model of how education works, of how children behave, in order to help you diagnose the problem and identify and implement a solution there. In programming terms, we call this debugging. The lady in the middle of the photograph here is Grace Hopper. It was one of the very early computer programs. You can tell it's a very early computer program which she's working on here. Notice that we do have a QWERTY keyboard and some sort of printer arrangement, so not absolutely the very earliest days. And the story goes that the program that Grace was working on didn't work, it didn't function properly, it produced the wrong sort of output. So Grace obviously has to identify what the fault is, what's caused that failure for it to operate correctly. And it turns out that there's a little insect, or bug as our American cousins would call it, which has crept into one of the relays, which is stopping the switch contacts from being made. And so removing the insect, or debugging the relay, allowed the program to function. So Grace wins her place in the archives of computer history as the first person to debug a program in that literal sense of removing the insect, the bug, from the electrical relay switch. But these strategies, it's not simply a case of finding the insect. There's a whole range of things, and those sort of pragmatic programming crowd advocate a whole range of things here that might help you when it comes to some of your scratch programming. So be aware of what you're doing. Look at the big picture side of things. And given that there are two of you working together, one of you focusing on the detail, the other focusing on the big picture, and taking in turns for those roles is a sensible approach to take. Don't code blindfolded. It's not simply about writing scratch instructions. Do be aware of the sort of big plan for this. And the more you plan your program, which is why I've wanted you to hand in this planning document and this storyboard, is such an important thing. Rely only on reliable things. What are the assumptions you make when hunting for the problems? And document those assumptions. Test the assumptions that you make. Are those actually reliable things? And testing your code. We've done that a lot of the time when I've been demonstrating things up on screen. Prioritize your effort. Remember, for this module, it's a notional 200 hours of work that you put in here, but that's not an infinite amount of time, and so concentrate your effort on the things which really do matter. It's hard for you to be a slave to history if you've never done any coding before, but do be creative and don't feel you have to do things the same way as I do when I'm demonstrating something. Ask yourself if there are easy ways to get things done. Ask yourself if the problem itself is the right one to be solving, and try and identify what's causing the actual problem and what makes it a difficult problem to solve. These last two are really, really sensible ones. If you don't get very far that way, then do ask yourself the question, do I have to do it this way? Is there another alternative approach to getting something done? And if the worst comes to the worst, does it have to be done at all? Can you not change that part of your game to something which might be easier for you to create? Yes, having an ambitious game matters, and I do want you to be ambitious with this, but actually having a working game matters even more, and that will be reflected in the mark scheme. I very much recommend Andy Hunt's book, Pragmatic Thinking and Learning. He's one of this pragmatic programming crowd. What he's done with the book here is to look at the whole process of thinking, of learning, of education in that relatively broad sense from a programmer's perspective. So whereas you're coming at programming from a teacher's perspective, or trainee teacher's perspective, he's doing it the other way around, coming to a lot of learning theory from a programmer's perspective. It's a really nice perspective on this, and perhaps quite a nice contrast to some of the other education texts that you're reading as part of the program. One of the things he talks about is this sort of left-right brain model, and there is evidence, I think, from neuroscience to suggest that this is not an entirely daft way of thinking about things. And the left hemisphere of your brain does all of this sort of linear, logical sort of thing. You know, it's very much where the verbal processing happens, your analytical skills happen over here. Because it's where the verbal side of your thinking happens, it tends to also be the rational side of things, and thus the logical side of things. So, you know, we're very much proceeding according to a set of rules. It's very much something which is easy for us to articulate. On the other side of your brain is a whole other collection of things which don't fall into quite such a sort of rational, verbal sort of mode. So when you're thinking in pictures, you're more likely to be on this non-verbal R side of your brain. When you're thinking in terms of spatial things, then you're over here as well. And you're less conscious, I would suggest, of what's happening here over here on the right-hand side of your brain. So if you're getting bogged down as you're working through on these left side, left mode strategies and approaches to solving problems, then trying to switch off the left mode and let the right mode take over and produce solutions for you which aren't rational, which appear to be something which just pops into your head. It's actually just popping over from one side of your head to the other. It's a reasonably sensible strategy. So often when planning lectures, what I'll do is I'll think about it just before I go to bed in the evening, and then let that right mode of my brain mull over that problem, and then first thing in the following morning the left mode can do the sort of analysis and rationalization and verbalization of that. But you may have your own strategies. But sleeping on things, going for a walk and not thinking about things, sometimes is a way of letting that right hemisphere mode pop into place. Brian Eno is a contemporary musician. He has a whole collection of these things as a set of cards. They're called his Oblique strategies. Let me show you one of these. Just selecting these at random. Nobility, of humility, of credibility. Is it quite possible? After all, don't be frightened to display your talents. Humanize something free of error. Look closely at the most embarrassing details and amplify them. So you might see these as relatively silly things, but you know, this sort of just almost semi-random suggestions can often help free up your thinking so that you can be more creative in your solutions to problems. Right, I don't want to say very much more in terms of problem solving. We're going to have a look at a couple of things when we come in for the session. So we'll do the obvious thing about coding up a maze game in Scratch, and that's something which I know a lot of you are wanting to incorporate in your game, and hopefully somebody will recognise where this is a picture of. If time allows, I'm going to have a look at how you might code up a jigsaw puzzle game in Scratch, which is another approach to another type of problem to solve, or a puzzle to solve. And then in time for next week's lecture, which is going to be slightly different in format, I'm going to ask you to read Ben Williamson's article on computer games, schools and young people. So I think that's pretty much all I wanted to say for this recording. Do post up a question on these matters or some of the readings in relation to this into the Blogfolio space. And we'll spend a little bit of time, probably not as much as in previous weeks, talking about those in the session.